Okay, so today we're moving into applications of differentiation. So this is kind of the chapter where we're going to culminate with optimization, right? So we're going to, at the end of this thing, our goal is what we're going to get with this is we're going to be able to take functions that can be modeled mathematically. They might be things like they could even be geometric things, but they could even be things like economics, where you want to be able to take a function. For us, we're going to have to be able to write it in terms of a single variable, but later on in life, you'll be able to model a function of more than one variable. And we're going to be able to find the values of the independent variable that optimize the output. Okay, this is a very valuable thing, right? And you want to be able to know, for example, if you were running a business or you were responsible for making decisions about, let's say, production for a company, there would be some components, like you might, for example, if you're selling widgets, right? That's always what they say in an econ class, I always call it a widget, just some random thing. But you're going to want to be able to make your decisions, like if you're in charge of setting the price, for example. So you want to be competitive, you want to set the price, you want to be able to set the price so you are going to maximize your profits, right? And you really don't want to necessarily maximize profits. You want to reach the point of diminishing returns when you're at an inflection point, but you don't necessarily want to maximize profits. You want to just be at a point where profits are continuing to grow, but they've started to grow at a decreasing rate, and so that's where you want to sit. Okay, I mean, for various reasons, but there's a lot of interesting calculus that goes with economics. So anyway, this is the kind of thing that we're going to start to introduce, this way of thinking. And it's probably easier to think of in terms of like one of the problems we'll do is something like, for example, let's say you've got a pasture that runs along a straight river, and you're going to you want to fence 3 sides of the pasture. This is very environmentally poor practice here, but let's say you have 3 sides of fence, the river's the other side, and you have a certain amount of lineal fencing, so certain feet of fencing, you're going to make a rectangular pasture. You might want to decide, okay, well, how am I going to get the most bang for my buck here? How am I going to maximize the area with the fencing that I've got? Well, that's calculus problem. You want to maximize area as a function of the dimensions of the fence, right? We can pick a specific dimension, like how far back from the river would it go, and that's going to impact how wide it is. Because I only have, let's say I have 300 feet of fencing or something, right? So that's our goal at the end of this unit. We want to get to that point. Well, to get to that point, we have to go through some. We have to learn about how we can connect differential calculus to a function in ways that we haven't really talked about yet. One of them is, and today's topic is extrema, right? So what is an extrema? Anybody know? 2 kinds of extrema. There are minima and maxima. So you know about these things. Extrema is the plural of extremum. A maximum of a function is what? I'm sure you've in some context talked about this.
I just don't remember.
Okay, like it could be a parabola, for example. A parabola that opens down would have a point, the vertex in that case you could describe as being a maximum. At some point I'm sure you did that.
Yes.
A parabola opens up, you could describe the vertex as being a minimum. Okay? Each of those are a type of extremum. One is a maximum, one is a minimum. So it's a little more complicated than that, though. We got to be able to discuss it in a little more detail than that, right? So we're eventually going to introduce some other vocabulary. And these all could be related to this fictional band called Extrema, this 80s hair band. So one thing we want to know is, Extrema is the name of their eponymous first album. Relative Extrema we're going to talk about today. That's their second album. Global Extremum is their world tour album, I guess, and then Absolute Extrema is their greatest hit. So they're a 2-hit wonder, 2 albums. But those are the 4 vocabulary terms that we want to be able to explain and understand, right? They're all different ways of talking about these points on a function that are important for us to find. Okay? So first of all, this is just out of our textbook, right? Definition of extrema. So if f is our function, is defined on some interval I. Now what does that mean? Some interval I. That means for some span of values of x, right? So some part of a domain we could generate, right? We're going to define the domain. If it's defined on some interval of x values containing the number c, so c is an x value. For example, it could be the closed interval from a to b, where a is the left endpoint and b is the right endpoint of our interval. That make sense? Okay. We would say that f of c is the minimum of f on this interval I, if what's true? If f of c is less than or equal to f of x for all x in I. I want you to just, this is a good thing for us to do at this point in the class, for us to take some language from a textbook and really try to connect the concepts to the language, right? Because you're going to do more of that in college. So I really want you to think about this and ask questions and see if we can make sense of this. Does that statement number 1 make sense? So f of c is the minimum. That's the smallest value of the function if f of c is less than or equal to f of x, which represents all values of the function for every value of x on that interval, right? That makes sense, doesn't it? That's the lowest value you could get. And we say f of c is the maximum of f on that interval if the value of the function at c is greater than or equal to the value of the function for all the other values of x on that interval, right? Okay? So the minimum and maximum of a function on an interval are the extreme values, or extrema. The minimum and maximum of a function on an interval could also be called absolute extrema. So if we're going to restrict this to a specific interval, like for example, for values of x greater than or equal to a and less than or equal to b, when we're talking about a specific interval, then we would use the terminology absolute. Okay, it is the, on that interval, I could point to that and say it is the highest value or the lowest value on that interval. It might be a shared, it might share it with other points, but there's no other point that's higher on this interval, no other point that's lower if it's a minimum, absolute minimum. Okay. Sometimes we use the term global. Well, global is if we expand that further. Global, typically in math, we use that to describe if we take the entire natural domain of a function. So it's not restricted. The domain on which the function, the largest domain on which that function could exist. So for example, for a natural log function, what's the natural domain of a log function? What's the graph of a log function look like?
0 to...
Yeah, it just does that, doesn't it? It's asymptotic on the y-axis, and then it goes forever. So the domain of this function, its natural domain, would just be like that, right? What's the natural domain of any quadratic function? Yeah, all reals, right? Okay. So for something to be a global extremum, it would have to be the absolute highest point that could exist mathematically on that function, right? So if you had a parabola, for example, a parabola can only have one extrema, or extremum, right? It never turns. The only way, I guess it turns once, right? So if the parabola has a negative value of a, then its maximum, the vertex, it's a global maximum. There's no other place mathematically on that function, on its infinite domain, where it could ever be higher. Agreed? Okay, so there's some terminology here. Now, if we're going to talk about intervals, let's look at some pictures. So what about this function here? Here we've got the function f of x equals x squared plus 1. So that's a parabola. It goes forever on its natural domain, but here it's been restricted. Here we're talking about the specific closed interval from -1 to 2. Okay? So on that particular domain, does it have a minimum? It does. The minimum is at the vertex. And so here's a case where we would call this an absolute minimum because we're talking about a specific domain. Okay? Does it have an absolute maximum?
No.
It does. Right there. Because that's the end of the domain. Right? Here's a way to think about that. If an ant were walking along this function on this specific domain, is there a place the ant could stand and say, I am at the lowest possible place on this domain? Yeah, it'd be right there. Is there a place where the ant could stand and say, I am at the highest possible point on this domain? Right there. So that indeed would be an absolute maximum. Okay? How about this case right here? Does it have an absolute minimum?
Yeah.
It does. Does it have an absolute maximum? How come? It's open. Okay, so, but, oh, I get you, but, so it can't stand on the point x equals 2, but why couldn't it just stand on the point next to that and call that the maximum? Oh, okay. So there is no point next to that one, is there? That's pretty bizarre, isn't it? Ponder that one for a second. Think about that. There's no point next to that open endpoint, right? There is no maximum. There's no place you would never, and that's the example. Remember the thing with the door we did at the beginning of the year, we talked about limits? Same deal, right? If I'm cutting my distance to the door in half every second forever for the rest of eternity, mathematically, I never get to the door, but I'm always moving, right? So I never get to a point where I can stop and say, okay, I'm at the point next to the door. There isn't. I'm just taking smaller and smaller steps all the time, right? So this is a case where we'd only have an absolute minimum, and here's a case where we'd have neither an absolute, we wouldn't have an absolute minimum, but we'd have an absolute maximum, because there's a hole at the vertex, okay? Get the idea, okay? All right, so extreme value theorem. This is, we're starting to get into some of the existence theorems in calculus. And these existence theorems, they're theorems that just say if you meet certain criteria, then it guarantees the existence of something. You still might have to go find it, but it guarantees the existence of something. So here's all this one says. Now I want you to ponder this. You're going to explain this to me, why this is the case. So if I've got some function, and the function on the interval, the closed interval from a to b, so if I take the value a, that's going to give me some point on the function, right? The coordinates of that point are going to be a, f of a. Okay, if I take the maximum x value in my domain b, and I look at a point on the function there, well, there's going to be some point with coordinates b, f of b. What the extreme value theorem says is that, here's the important part, if f is continuous, then f has both an absolute minimum and an absolute maximum on the interval. Can you disprove that? Is there a way that couldn't be true? Has to be true, doesn't it? Right? There's no way around it. There's no loophole here. Think of all the things that could happen. Well, I could have a function that does something like that, and there's the absolute maximum and there's the absolute minimum, right? Well, it might be that the function has two equally high peaks. Maybe it does something, that was a bad one. Maybe it has two equally high peaks, so it goes up like that. If they're at the same height, then that's a shared maximum, right? It has a maximum y value, happens to reach it twice, okay? What if it doesn't have any peaks at all? What if it does this? Where's the absolute minimum? Right there. Where's the absolute maximum? Right there, right?
I thought it's maximum.
Okay, and we could even, maybe you're thinking, okay, how about this one? How about this one? What if this is my function? Every point is a minimum and a maximum, right? There's no way around it, right? The only way I could possibly come up with a situation where there's no minimum or maximum would be if I did something like that, maybe, right? But I broke the rules. It's not continuous. Okay? So there's the extreme value theorem. If f is continuous on a closed interval, it's guaranteed to have both an absolute minimum and absolute maximum, so our job in calculus is to find those. So definition of a relative, sometimes called a local, a relative or sometimes local extrema. Okay, if there is an open interval, now we got to really think about this one too. If there is an open interval containing C on which f of C is a maximum, then f of C is called the relative maximum of f. Okay? So does that mean it has to be the highest point anywhere on the function? No. It just means that there's some open interval on this function containing C where it's the highest place on that interval, locally speaking, right? There could be other places where it's much, much higher, but on that interval containing C, it's the highest. So what's that going to look like in terms of the topography of the function? If I were to graph this function on the board, you'd be able to recognize it because it would look like what? What do you think? If it's the highest place on that one interval, what's its shape going to be on the graph? Okay, it's going to be something maybe like that, right? It's going to be a peak. It's going to look like a peak. Okay? So a relative maximum is always going to be a peak. That's what it's going to look like. Does it have to be the highest peak? No. It has to be a peak. Relative to the places around it, it's the highest. In other words, if we're using our ant analogy, if an ant walks to the left or the right on the function, he's going to end up at places lower than he was. Right? Isn't that the definition of a peak? Okay, so if there's an open interval, obviously, in which f of c is the minimum, then it's a relative minimum. What's that going to look like? A valley. Yeah. Okay. Essentially, a relative maximum is a peak, and a relative minimum is a valley. Okay. Oh, something else I just want to throw in there. So the word open interval is thrown out there. An open interval would be something like this, right? Okay. So what is an open interval then? An open interval is all the values of x between the endpoints. So how many more points does a closed interval have than an open interval? 2. That's it, right? That's it, just the left and the right endpoints. Okay? Okay, so what about, let's say we want, on some open interval here, we want to graph a two-dimensional topology that's going to show me relative maxima and relative minima. Okay, what kinds of peaks could I draw? So if I'm starting at this end, that's a peak that I could draw, right? There's a valley I could draw. But I could also draw peaks like that, and valleys like that. So those all have to be included. Here are relative maxima. Right? And they're about the same height. They don't have to be. One could be much higher than the other. And here are examples of relative minima. Can you connect those to calculus, the derivatives? Okay. So where a slope is 0, what does that mean on a function? Okay, so but where the slope is 0, slope is equal to, the slope of a function means the slope of a tangent to the function, slope of a tangent line to the function, right? So how would you describe a tangent line that has slope of 0?
No, it's
Horizontal, right? Okay, so one place that this could happen is where we get horizontal tangent lines, which means those are places where if this function is f, those are places where f prime is 0, right? Okay. What about the other species, though? What about these sharp peaks and valleys?
You can't do that,
How come?
because you can't, it's not tangent,
You're right. And think about the places where derivatives don't exist. If you go clear back, many, many months ago. Sharp corners, right? So if you have a sharp corner, the derivatives don't exist there, right? So here are examples right here and right there. Those are places where f prime does not exist. That's helpful to know, right? So if we're trying to look for these places, these relative extrema, where are we going to look? The only types of relative extrema that we could possibly have would be this type and this type, right? And both of those occur at places where the derivative has specific values or where it's not defined. Either it's 0 or it's undefined, okay? So types of relative extrema. So we could get something like if we look, for example, at this function. Okay, we've got this function, f of x equals that. I'm not going to say it, you can read it, right? That function, we can see from the graph that this function has a relative maximum at 3, 2. How come? How come? Well, because that's a place where the derivative is equal to 0, right? Okay. How about this function? And look what happens here. If we look at f prime of 3, and you can do this on Desmos, it's pretty cool. If I define the function, if I use the notation f prime, if I do f prime of 3, it's literally going to calculate the derivative of that function at that place. And look, it's 0. Okay? How about this one? We've got an absolute value function. That's obviously a relative minimum, right? We can see that's a valley. How come? What's going on there? Well, f prime of 0 is undefined. Okay? How about this guy? If I take sine x, for example, f of x equals sine x, then f prime of pi halves is 0. Look what we get. We get a horizontal tangent there. F prime of 3 halves pi is 0. We get a horizontal tangent there. Okay, so we got these two different kinds. We're going to get peaks where the derivative is undefined. We're going to get jagged peaks where it's undefined, sharp peaks, and we're going to get smooth peaks where the derivative is 0. Okay, same thing for valleys, right? I get that one backwards, but you get the idea. Okay, so does it make sense then, if I'm in my search for a relative extrema, peaks and valleys can only occur at places where the derivative does one of these two things, right? So if we're trying to look for peaks and valleys, which is what we do in calculus, in differential calculus, how are we going to look for them? What are we going to do? If I've got a function and I want to find all the places on the function where it has peaks and valleys, relative extrema, what would your strategy be? Okay, take the derivative and then ask the math gods, where does the derivative equal 0 or where is it undefined? And that's what we're going to be doing for the next few weeks, right? Is doing just that. We take a derivative and then we algebraically have to go find the places where it equals 0 or where it's undefined. We call those places, those values of x, we'll call those critical numbers. So relative extrema occur only at critical numbers. And there's two types of critical numbers. We get critical numbers where the derivative is 0 and where the derivative is undefined. And we've already seen examples of both of those, right? Okay? But are all critical numbers that we find necessarily going to give us relative extrema? Could there be places where a derivative is undefined or equal to 0 that don't produce a peak or a valley? Well, yeah. Yeah, you could. I mean, you could have a hole, yeah. But what if it's even a place where the function is continuous? Let's even make it, I'll stipulate that, so we're going to be more restrictive here. If it's a place where the function is continuous, could you still find places where you get a critical number that does not yield an extrema. So we want to draw, see if you can draw one for me. Double dog dare, anybody think they can draw a situation where?
No,
Anybody want to try it? Well, tell me what to draw then? You're
no.
bashful?
I will, some sort of application.
I'm just gonna draw a picture of a function. I just want you to draw, so what could a function look like that has a critical number, which would be a place where the derivative equals 0 or is undefined, but that critical number doesn't give you a peak or a valley. Got an idea?
Go for it, Seth. Do what you
A log. Let me see if I can spell. Square root.
X to the, okay, x to the third. What if I do x to the third? If I do cubic? What's the slope of the function there? What's the slope of the tangent line? If I drew it properly.
0.
Right? See what I'm saying? There is a horizontal tangent there, but it's not a peak or a valley. Okay? So it failed. Okay, well, how about a sharp corner one?
Absolute value.
Absolute value is a minimum. But I'm not gonna try to come up with a specific function, but what if I had one that did this? What if I had one that went like that? That's a sharp corner, right? And yet it's not an extremum, okay? So the moral of the story is, if we're looking for extrema on a function, you'd be vigilant. Yeah, you're gonna find all the critical points, or the critical numbers, right, where the function has a derivative that's undefined or equal to 0, but can I always assume that all of those are gonna produce extrema? No, I'd have to check them, wouldn't I, right? I'd have to check each one of those to see if they actually work. And we're gonna come up with a couple of good tests for doing that. And going into this, I will tell you that of all the things I hear from students when they go to college, the thing that I believe is the thing that we do in this class that's somewhat unique compared to maybe the college class. And this is the one you want to really take good notes on, and you'll get this one. But there is a tabular way to organize your search for interesting places on a function, for extrema, and then we're also going to learn how to find inflection points, which we're not going to talk about. That's a second derivative thing. We're not going to talk about that for a while. But there's a way you can organize it on a table that makes it really easy to to search for those places and find them. And so when we talk about using tables in class, man, that proves very helpful in college. Make sure that you get good notes on that stuff, because you'll use it, I promise you. So not all critical numbers yield extrema. Here's an example we looked at. Here's another one. How come that derivative's not? How come that's a false alarm? What's going on with the derivative there? Undefined, how come? Vertical tangent, right? What's the slope of a vertical line? It's undefined, right? So there's another place where the derivative would be undefined because I have a vertical tangent line, but it's not an extremum, okay? And there's the example of a cubic function, right? The slope of the function right there is 0, but clearly it's not an extremum. Okay, and there's another one. Okay, where the slope or the derivative is undefined, okay? So this is, I'm gonna throw this one at you. This one doesn't show up in a lot of textbooks, but I think this is kind of a cool one. I think this is one that if you go on in math, you'll see this again. Fermat's theorem is one of his theorems. Says if f has a relative extremum at C, and f is differentiable at C, then what? What does it mean to be differentiable? What's it mean? That you can take the derivative, yeah. So this word right here just means you can differentiate. Right? Differentiable. So you can take the derivative of them. So if f has a relative extremum at C and it's differentiable, then what can you tell me about that extremum? Okay, but what's that tell you about the nature of that extremum? Okay, yeah, it's got to be curved, doesn't it? Right? If it has an extremum, then doesn't that mean that the derivative would have to equal 0, right? Okay, that's so profound. Okay, so summary. Relative extrema, peaks and valleys. Absolute extrema, maximum values and or minimum values on a specific interval. Global extrema, the maximum values and or minimum values of a function on its entire natural domain, right? Okay, why did I put this up here? I can't remember what my thinking was on this. I can't remember. I don't think it was that profound. Okay, so then, next issue. So let's focus, we're going to focus for a while on finding absolute extrema, and then after that we'll look for other types too. So if f is a continuous function over a closed bounded interval I, closed interval, then where must the absolute extrema occur? Where's the only place they could occur? So I've got an interval from A to B, including the endpoints. The highest and lowest points on the function would have to occur at what possible places? Let's say it again.
In between A and B.
Sure, but what are the, if we want to be more specific, what are the only places where the function could have its highest or lowest value on a closed interval? Peaks and valleys could be, right? So peaks and valleys always occur where? At what kinds of numbers? Critical numbers, right? So one place that they could occur is at critical numbers. Where else? On the endpoints too, right? They could also occur at endpoints. So if I gave you a closed interval and I said find the relative or find all the absolute extrema, what are the only places you'd have to look? You'd have to look at the endpoints and at the critical numbers and just compare. Really, you can do this right now. What would you do? You'd find those values and plug them into the function, and the biggest values, the maximum, and the smallest values, the minimum, right? You can do that right now. So our guidelines then for finding absolute extrema on a closed interval are pretty simple. We're going to find all the critical numbers of the function on the open interval between the endpoints, right? We're going to evaluate f at each of the critical numbers that we find. We're going to evaluate f at each endpoint and see what the biggest and the smallest values are, right? And we could do that in a table. So here's your first introduction to tables. So we could do that like this. If this is, if this is x, this is my x row. Oh, let's back up. Think of that as being the x-axis. I'm going to put a row in my table for x values. Okay? Let's say that we're looking for the absolute extrema on the interval of f on the interval from -1 to 4. Well, then the x values that I would consider would start at -1 and end at 4.
Do they have to be whole numbers?
Say it again?
Do they have to be whole numbers?
No, they could be anything, just numbers. I just pick convenient ones. Okay.
I just didn't know if like 1.27 would be extreme.
Well, it could be. Could be. Or it could be a square root of 2, or it could be, it could be all kinds of things. But then I would find all the interior critical numbers, and let's just say hypothetically that I found critical numbers at x equals -2, x equals 1 and x equals 3. When I find the places where the derivative is undefined or equal to 0, those are the 3 places I come up for my function. What do I do? Well, -2 is not on my domain. I don't care. But 1 is, so I'm going to put in a 1, and I'm going to try to keep this so it's, so I'm spacing them out roughly where they should be. And there's 3. Would you agree that those 4 x values are the only candidates for absolute extrema? Right? So what do I do then? I make another row in my table. For f or y. And I'm just going to figure out, well, what are the values of the function at all those places? So let's just say that I evaluate the function. And I find that when I plug in -1, I get a value of -5. When I plug in 1, I get a value of 0. When I plug in 3, I get a value of 4. And when I plug in 4, I get a value of 1. Look, these are just like ordered pairs. Right? So these are just ordered pairs. They're just written vertically instead of horizontally. What's the absolute maximum of this function?
3, 4.
3. The absolute maximum is 3, and it occurs at the point 3, 4. Okay? What's the absolute minimum? -5, and it occurs at the value of x, -1. Okay? What we're going to do with this in the future is we're going to add additional rows to our table. F prime and F double prime. And the information that we get from those rows is going to tell us tons of stuff about this function. And the goal is, right before we jump into optimization, we're going to take a test on curve sketching, where you're going to be able to take all this information and sketch a pretty accurate representation of what the function looks like. Does it have to be exact? No, but I do want to know the locations of the important points, right? That's an important thing to be able to do. All right. Okay, we're done for today. Are we out of here like in 5 minutes, 4 or 5 minutes? Okay. That's enough to think about. So I'll put up some assignments, but we're gonna just have to we'll just kind of inch forward a little bit every day for a few days.
That's really cool.
And you all like pretended to come up and wipe your hand on my face on the day before you left.
That's coronavirus.
And you were really sick.
That's fever 102.
When I get sick, I blame you.
So what's the word on the coronavirus today?
And there's like 10,000 people in there.
First person in America to transmit it so well.
Yeah,
Yeah.
that's bad.
It was in
In
Illinois.
Illinois?
It's also,
Some
there's
school brought it to their
two
Yeah.
people in
Well,
UK.
Fox, right up to Texas.
In UK?
Yeah.
Yeah, there was
Wait,
this
what is
particular on the board she had that it said it was like
California, or Washington.
9,800 people that are infected.
In China.
No,
How many have died?
I don't know.
213 or something.
Yeah.
Man,
And I think
that's-
that's only in China. Like they've only done.
yeah.
Even though it's only
Yeah, no
like
one's
that.
out of the US yet.
Even though it's only like
And
that.
there's 6 people in the US that are infected.
It's the same as the
But
Spanish
it's only
flu.
in Washington, California,
We're healthy.
California, Arizona, and Illinois.
Yeah.
And really?
Yeah.
She doesn't have it.
The only one that's been transferred
Yeah,
is
Is
Maryland
Maryland.
has been there.
They started catching it, so
Yeah.
go worldwide.
There's also maybe starting at the
Last night there was 2 cases in Chicago, 2 cases in California, 1 in Washington, and 1 in Arizona.
Wow.
I also found out that there's 7 different types of coronavirus.
Oh yeah, SARS is a coronavirus.
Yeah.
Yeah.
So it's been around for a long time.
Yeah.
When Zoe's dad was getting tested, he had to be tested for coronavirus in
Mhm.
2016.
Yeah.
It's like,
But now,
Oh, yeah. But it's just, this is a different kind of.
it's a new coronavirus.
Yeah.
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 So I thought I heard that this one now it's either it's mutated or they've just found out that it can be transmitted. It doesn't have to be person to person. It can be like the
it's airborne, that's,
not. I don't know if it's airborne, but the virus can live on doorknobs and it can live on inorganic objects for a while.
it's plague or
They
what?
said it can be spread by
Yeah, and I know that's, yeah, close contact.
Area 51.
Well, I don't think this one's gonna prove to be something that's gonna end up being a global pandemic of epic proportions, but that's probably what's
The
gonna,
number of people
what's gonna get us is gonna
already
be a
high.
global pandemic.
Total number of people infected is already higher than SARS.
Yeah, oh yeah, and the rate of transmission is much higher, yeah.
That'd be a pretty diverse person.
It's only like a 5% mortality rate, but
Yeah.
I mean, the Spanish flu was a 5% mortality.
Yeah,
It killed you.
5% of
And
sick bay people.
this is a lot of people, yeah.
That'd be a very
Yeah.
interesting person.
And you don't,
Yeah.
yeah,
Like, both the most tolerant person to ever live, but also just really.
yeah, that's pretty crazy.
I don't wanna die.
It's one of the problems that we're gonna have is that the vectors for disease transmission are changing because of climate change. Lots of these diseases that were considered to be only problems of the tropics are becoming, even at moderate latitudes now, are becoming much more prevalent. That's gonna be a problem.
It's because we're reawakening.
Here's a map